In this video, we will see about the steady state analysis of a single phase fully controlled rectifier fed DC drive. So this is the single phase fully controlled rectifier. We know a fully controlled rectifier consists of 4 thyristors connected in a bridge fashion. So this converter can convert AC supply into DC output, and this DC output is given to the separately excited DC motor. So this is the field winding of the DC motor, which is given a separate DC supply, and this is the EB represents the back EMF of the motor. So by changing the firing pulses of this thyristors, the output of the fully controlled rectifier will change. So this output will be given to the motor. So by changing the firing pulses, we are able to change the voltage applied to the motor. So there are basically 2 modes of operation in a fully controlled rectifier. One is rectification, another it is inversion. That is, if it acts as a rectifier, it converts AC to DC, or the power flows from source to the load. So here the load is motor. It can also act as an inverter if it supplies the stored energy back to the supply. That is, DC to AC conversion takes place. So this converter will act as a rectifier when the firing pulse alpha is less than 90 degree, and it acts as an inverter when alpha is greater than 90 degree. We have 2 more modes of operation. One is called continuous conduction mode, where the armature current will flow continuously, and in discontinuous conduction mode, the armature current does not flow continuously. That is, in between it will be 0 for some time. In such cases, we call it as a discontinuous conduction mode. So if you see the period and the device, alpha is the instant at which we give the gate pulse for the thyristor. So alpha to pi plus alpha, T1 and T2 will be conducting, and from this pi plus alpha to 2 pi plus alpha, the other 2 devices will be conducting. So in this case, if we see, there is a continuous conduction. So the current continuously flows. Whereas if you see the discontinuous conduction mode, from alpha to beta, 2 devices will be in conduction, and for a small period beta to pi plus alpha, no device will conduct. That is, there will be a period for which there will be no armature current. So in such cases, we call it as a discontinuous conduction mode. First we will see about continuous conduction mode. In rectifier mode of operation, alpha is kept less than 90 degree, IA will be always unidirectional, and the motor load can be represented by a RLE load. And the important thing to note here is that in RLE load, the SCR will turn on only when this supply voltage is greater than the back EMF E, because this is a DC voltage and this is an alternating voltage which will change its magnitude every time. So when this magnitude is greater than E, the device will be forward biased, and after that if you give gate pulse, the device will turn on. So in case of RLE load or motor load, this condition should be satisfied. That is, Vm sin alpha should be greater than the back EMF, so that the device will get turned on. So in case of T1 and T2 conduction period, you can see here when the supply voltage is greater than EB, the device will start conducting and current flows through T1, load, T2 and again to supply. So now we will consider the continuous conduction mode. From alpha to pi plus alpha, T1 and T2 are conducting. First make sure that alpha is here. See this? You have to give the alpha after this junction. This is supply voltage which is changing its magnitude, and this straight line is the back EMF. When the supply voltage magnitude is greater than back EMF, you have to apply the gate pulse. So T1 and T2 are given gate pulse after this junction. Okay. So T1 and T2 will conduct from alpha to pi plus alpha. So this point. So at that same instant we are giving gate pulse for T3, T4. So T3 and T4 will start conducting from this period to again 2 pi plus alpha. So the current will be continuous in this mode. So it is given by a waveform like this. This one you can draw it as a straight line also, because in some books they might have given it as a straight line, because if you consider this inductance as a very high value, you will get a straight line. So you can draw it like this also. Next we will see about inverter mode of operation. So inverter mode, two conditions are there. One thing, alpha should be greater than 90 degree. Then the important thing is this back EMF should be reversed. That is, the polarity of this back EMF should be reversed. So in previous case it was plus there and minus here. Now we have changed the polarity. So how to get reverse this polarity? Back EMF, we know it is directly proportional to Km into omega m. So if you reverse the speed, you will get the reversal of back EMF. So this concept, this inverter mode is used in regenerative braking of DC motor. So let us draw the waveform for alpha greater than 90 degree. Again we have supply voltage, and EB, you see the direction is reversed here. So it should be drawn in the negative direction. And you see the polarity, it should be minus plus. So here it is here. Now the firing pulse should be greater than 90 degree. So you are giving firing pulse here. That is, after 90 degree you give the firing pulse, then it will follow the input waveform. Okay. So this table remains the same. Only thing, we are delaying the alpha, and the current will also be continuous. Here also you can simply draw a straight line to show it is a continuous current. Let us derive the average voltage now. V average is given by 1 by pi. That is, we are writing for half cycle. Alpha to pi plus alpha, output voltage is Vm sin omega t. So simplify it. So integral of sin omega t is minus cos omega t. Apply the limits. You will get 2 Vm by pi cos alpha. So the average voltage is 2 Vm by pi cos alpha. So let us plot this one here between output voltage and alpha. So what happens if you change the alpha, how your average voltage will change. So let us do the calculation here. So when alpha is equal to 0, cos 0 is 1. So V0 is equal to 2 Vm by pi. When alpha is 45 degree, V0 is Vm by pi, and when alpha, that is cos 90 is 0. So your output voltage become 0. And if you give alpha 180 degree, it is cos 180 is minus 1. So you will get minus 2 Vm by pi. So now let us plot this one. So you can see here for 0 to 90 degree it acts as a rectifier. For 90 to 180 degree it acts as an inverter, and its voltage changes from 2 Vm by pi to minus 2 Vm by pi. Next we will derive the relation for speed torque equation. So we have derived the average voltage. V average is equal to 2 Vm by pi cos alpha. We also know this armature voltage in a motor is equal to Eb plus Ia Ra. So this is motor equation. This is the converter output equation. So this converter output becomes the input for motor. So we are equating these two equations. So from this you know back EMF is equal to Km into omega m. So you find omega m from this. So that omega m is equal to this term divided by Km minus Ia Ra divided by Km. Now we want torque equation. So what is torque? Km into Ia. So instead of Ia you substitute torque divided by Km. So here instead of Ia T by Km. So omega m will be equal to this one minus I. Instead of Ia you put T by K. So you will get this one. So this is very easy to derive the speed torque equation because it will be same in all the converters. Only thing, if you know the average voltage, just equate to Eb plus Ia Ra for all the converters. So now we will find the no load speed for both rectifier and inverter mode of operation. So what is no load condition? It means that the armature current is 0. It means that none of the devices are conducting. Current is 0 means no device is conducting. So we have already seen that when the supply voltage is less than the back EMF, devices will not conduct because it will be reverse biased. Device will be reverse biased. So for alpha less than 90 degree, that is rectifier mode, when Eb is greater, that is when the back EMF is earlier it was here, suppose the back EMF is here, wherever you give the gate pulse, the device will not conduct because back EMF is greater than the supply. So under this condition, Ia will be 0. So from this relation, we can find the no load speed. So Eb is equal to Km into omega m. So we can write omega m naught equal to Vm divided by Km. And for inverter mode of operation, that is for alpha greater than 90 degree, Eb, that is this is 90 degree. For this region, if you want to give the gate pulse, Eb should be greater than or equal to Vm sin omega t means it will not conduct. Devices will not conduct or Ia will become 0. So for finally you can conclude that the omega naught no load speed will be equal to Vm by Km for rectifier mode, and it will be equal to Vm sin alpha by Km in case of inverter mode. Next we will see about discontinuous conduction mode. So discontinuous conduction means armature current is not flowing continuously. So when you will get this type of condition, when you have low value of inductance or large, your firing angle is so large that your conduction period is very less and load is very low means it will take only less current. So in such cases current may become discontinuous. So this is the waveform for discontinuous conduction mode. So same supply voltage waveform and the back EMF is there. Here this output waveform has two periods. One is the conduction period and another is called idle period where the current is 0. You see here current, this is the armature current waveform. It will increase and it will become 0 for some time. That period is called idle period. So if you see the output waveform, alpha, you are giving the firing pulse for the devices, so it will follow the output voltage waveform till beta. At beta, the armature current becomes 0, but you will give the gate pulse only at pi plus alpha. So till that point, beta to pi plus alpha, none of the devices will conduct and the output voltage will be equal to back EMF. Okay. When you give the gate pulse at pi plus alpha, again T3 plus T4 device will conduct till again this beta, and after that there will be a short period for which current will become 0. So two periods will be there. One is conduction period and idle period where the armature current is 0. Now we will derive the average output voltage for discontinuous conduction mode. So you take half cycle 1 by pi. Your period starts at alpha to beta. Output voltage is Vm sin omega t, and from beta to pi plus alpha it is Eb alone. Okay. So you simplify this one. So minus Vm cos omega t, limits are alpha to beta. For Eb, limits are beta to pi plus alpha. So simplify this. So this is the average voltage for discontinuous conduction mode. Next we will find the speed torque relation. Same procedure. You have V average equate to Eb plus Ia Ra. So simplify this one, you will get a relation like this. Now we will draw the speed torque characteristics. So it is drawn between speed and torque for different values of firing angle. You see here, for alpha equal to 0 degree, it starts from here, and this dotted line represents the boundary between the continuous conduction mode and discontinuous conduction mode. So here you will get at low values of torque, you will get discontinuous conduction mode, and after that you are getting continuous conduction mode. And for different values of alpha, your waveform will be like this. And at 90 degree, if you see, we know that it changes from, when alpha equal to 90 degree, it changes from rectifier mode to inverter mode. So this will come in fourth quadrant. This will for alpha greater than less than 90 degree, it will be in first quadrant. So there is a term called critical speed, that is the speed at which the motor enters into continuous conduction mode from discontinuous conduction mode. So this single phase fully controlled rectifier operates in two quadrants, first quadrant and fourth quadrant. In first quadrant you are getting motoring operation. So this is the converter which gives an output of plus Va, and current is always positive Ia, and this is the motor back EMF E, and speed is in this direction. Okay, so for first quadrant operation, for getting a first quadrant operation in single phase fully controlled converter, alpha should be less than 90 degree, Ia is always positive, Va is positive. So Va and Ia are positive means power is positive, speed is also positive. So you will get forward motoring operation. So omega is positive, omega is speed is positive, so torque is also positive. So you are getting forward motoring mode. Next, to get the braking operation or to operate in the fourth quadrant, First we should make alpha greater than 90 degree. So if alpha is 90 degree, average voltage will be negative and IA will be always positive. So what happens to power? If you multiply these two, you will get negative power. And this back EMF, when we make alpha 90 degree, we will reverse the back EMF. So speed changes, speed is negative. So you will get speed negative, torque positive. So you will get the operation in fourth quadrant. So that is a reverse braking, or you can make regenerative braking in this mode. So the points to remember here are: single phase fully controlled rectifier fed drive, you can achieve two quadrant operation, that is first and fourth quadrant, that is forward motoring and reverse braking. And in continuous conduction mode, the average voltage is 2 Vm by pi cos alpha, and for discontinuous conduction mode, this is the average voltage. This equal to EB plus IA RA, you will get the speed torque relation. So if you like the video, do subscribe to Read Electric Vehicle channel. These are the sum of references which I have used.